The modern power grid operates as a massive, centralized hub-and-spoke network. Because everything is highly interconnected, a single point of failure, like a downed transmission line or a blown substation, can trigger a cascading blackout that takes out entire neighborhoods or cities. To escape this fragility, many homeowners install standard off-grid solar panels and battery banks. It feels like stepping off the grid and achieving total energy independence. But that isolated setup has a major inefficiency. On a sunny day, a home battery might hit 100% capacity by early afternoon. After that, any excess energy the panels generate is either completely wasted or sold back to massive utility companies at a steep financial loss. These isolated systems are also physically vulnerable. Standard solar setups rely heavily on cloud servers and AC inverters to function. AC, or alternating current, is the standard flow of electrical charge that periodically reverses direction to power regular home appliances. If the global internet goes down, or your main AC inverter fails, your entire home goes dark, even if the sun is shining brightly outside. Bridging dozens of these isolated setups into a unified, interconnected community microgrid establishes a layer of protection that no single home can maintain on its own. This diagram illustrates the primary barrier to building that community network. These abstract nodes represent different proprietary hardware brands, like Victron, SMA, and Growatt. Because they each speak completely different, incompatible digital languages, they cannot naturally coordinate or share power with one another. The path to community energy sovereignty requires solving the technical bottlenecks of hardware translation and local network coordination. To solve this, we have the resilient Microgrid Utility Bundle. At the physical core of this bundle is the Sovereign Sentry, a ruggedized, fanless edge compute node that acts as a local command center. The kit includes a step-down converter that wires the Sentry directly to a 48-volt DC battery bank. DC, or direct current, is the one-directional flow of electrical charge typically supplied by batteries. By bypassing the home's AC inverter entirely, the compute node stays powered and active even if the main inverter suffers a catastrophic failure. It also comes with opto-isolated adapters. These physical hardware barriers protect the Sentry from electrical surges up to 3,000 volts, preventing high-voltage equipment from shorting out the brain of the operation. Inside that rugged box runs the OpenClaw Foreman AI. When it boots up locally, it scans the physical ports and automatically detects exactly which brand of inverter hardware it is plugged into. This flowchart shows how the translation mechanism works. The Foreman takes in complex, raw industrial protocols like Modbus and CAN bus. Modbus is a standard serial communications protocol used to transmit data between industrial electronic devices, while CAN bus is a message-based protocol designed to allow microcontrollers to communicate without a host computer. The AI translates these disparate data streams into a single, unified, locally hosted grid state. By combining isolated power with intelligent translation, a passive solar setup becomes an active, hardware-agnostic control center capable of surviving severe electrical failures. Once a node is active, it shifts its focus to the surrounding community. Using a secure cryptographic certificate, the Sentry node connects to neighboring nodes over a local Wi-Fi or LoRaWAN mesh. LoRaWAN is a low-power, wide-area networking protocol designed to wirelessly connect battery-operated devices over long distances. This map illustrates a specific daily scenario on that local mesh. On the left, a local farm hits 100% battery capacity in the early afternoon. On the right, a town clinic is running heavy air conditioning loads and rapidly draining its own battery. Because they are connected, the farm's foreman agent continuously reads the clinic's state of charge. State of charge is a metric that indicates the current energy level of a battery relative to its maximum capacity. Instead of letting its excess power go to waste, the farm's node autonomously triggers the physical relay. It routes its overflowing solar energy directly into the clinic's shared water boiler, effectively dumping the power into thermal storage for the community to use later. To protect the physical hardware, the system uses hysteresis enforcement. Hysteresis is a logic safeguard that creates a deliberate lag between an input and an output to stabilize a system. Here, it strictly forces a 5-minute hold on any relay switch, preventing mechanical wear and tear if a fast-moving cloud briefly blocks the sun. Energy that would normally be lost is actively captured, converted into shared thermal storage, and used to strengthen the entire town's resilience. When an entire town equips its homes and municipal buildings with these nodes, it begins operating as a fully decentralized, self-sustaining mesh. The community achieves true sovereignty over its power. The network requires zero monthly software fees, utilizes no cloud APIs, and operates entirely air-gapped from external corporate servers. APIs, or application programming interfaces, are software intermediaries that allow different applications to communicate over the internet. This diagram demonstrates the system's primary defense mechanism, autonomous islanding. If the main power grid starts to fail and produces dangerous voltage-frequency anomalies, the nodes instantly detect the drop and command local inverters to physically disconnect from the microgrid. While surrounding infrastructure sparks and goes dark, the severed microgrid operates perfectly. Nodes negotiate with one another, circulating local solar and battery power along internal mesh pathways. Linking disparate residential and municipal systems transforms a collection of solo users into an anti-fragile community powerhouse that ultimately renders the legacy grid obsolete.